Yeah, there was a lot of notes. You have a lot of notes to get and a lot of videos to watch if you were not here last couple days. Okay, so we left off yesterday talking about the kinetic molecular theory that states that all matter is made of particles or atoms that are doing what? That are in constant motion. So everything's in motion, even solids that move just a little bit, like you're emulating solids because you're fixed in position, but you're still able to move a little bit. When the bell rings, you'll emulate liquids because you'll flow out the door. And if any of you emulate gases, that would be kind of cool. Jump really high. But the important thing to get from yesterday was intermolecular forces cause molecules to attract. The movement energy causes molecules to pull away from each other. So when you have a solid, which one wins? In the battle between intermolecular forces that cause attraction and movement energy, which causes movement away from each other, with a solid, which one wins? Yeah, the attraction. So solid particles, the intermolecular attraction is stronger than the movement energy. With liquids, they have pretty strong intermolecular attraction, but not as strong as solids. So the molecules have moved a little more. They're able to kind of overcome the attraction, but the molecules are still stuck together. They're just not fixed in place. And then with gases, what happens going from a liquid to a gas? To go from a liquid to a gas, what do the molecules have to do? They have to heat up and speed up enough that they break away from their intermolecular attraction. Gases have very low intermolecular attraction because the gas particles are moving so fast that they don't even realize each other's there. Okay? So we have very strong intermolecular forces, slightly strong, and then very weak. And to go from one phase to another phase, you speed up or slow down to either break away from those intermolecular forces, or if you slow down enough, intermolecular forces start controlling you and you get stuck in position. Give me a thumbs up if this makes sense and you're ready to move on to something new. Question?
Can you give what's intermolecular force in a definition way for an easier way?
Okay, just like magnets have a north end and a south end, and the north end of one magnet is attracted to the south end of another magnet, molecules that are polar have positive ends and negative ends, partial positives and partial negatives. So molecules that are polar will be attracted to each other. So if I gave you this magnet and you put another one on the desk and you went, oh, obviously the attraction is greater than the movement energy. But then if I gave you this magnet and I threw another one at you really fast, we'll see if they stick. You ready?
A little.
Okay. So is there a pretty good chance they're going to stick if it's moving really fast? No. Even if it hit it, it'll probably bounce off. So with a liquid and a gas, the molecules are moving pretty fast, so even if they get close to each other, they don't stick. On the other hand, a solid, the molecules are moving very slowly, so they do tend to stick. Okay? So the intermolecular forces are very, very strong, much stronger than movement energy in a solid. In a liquid, they might stick. Maybe they will, maybe they won't. With a gas, they're moving way too fast to stick. Always fun to have little, tools of opportunity. Magnets are right there. Okay, so ready to move on to something new? Something new. Lewis structures. Lewis structures are a neat way to draw a three-dimensional molecule on a two-dimensional plane, like a piece of paper. So Lewis structures are a way we draw a three-dimensional model of a molecule, but we do it on a two-dimensional piece of paper. They're very, very handy. Most of the molecules that you see out there in real life are actually Lewis structures. You see those molecules that have boxes and lines and hexagons and all sorts of molecules all over those? Those are all Lewis structures. We're going to draw some very basic Lewis structures. So this is what we do. To draw a Lewis structure, you take the molecule or the atom you're looking for, and you need to determine the atom's number of valence electrons. So when we're done scribbling, we're going to pause and look at our giant periodic table and determine how many valence electrons each thing has just as a matter of review. Okay, so follow the little green dot to the wall. How many valence electrons does all of group 1 have? 1. How many does group 2 have? Everything in group 2?
Yeah.
Yeah. Group 13? 3. Group 14? What about germanium way down here?
4.
Still 4. Nitrogen's group? 5. Oxygen's group? Even sulfur? Yep, even sulfur. And the halogens? 7. So group 1 has 1. Group 2 has 2. Group 13 has 3. Group 14 has 4. Group 15 has 5. Group 16 has 6. Group 17 has 7. 1, 2, 3, 4, 5, 6, 7. So chlorine has how many valence electrons? 7. And we're going to draw the valence electrons as dots around the atom. But here's what's really important. The dots are drawn clockwise. So we're going to start with 1 at the 12 o'clock position, then the 3 o'clock position, then the 6 o'clock position, then the 9 o'clock position, then 12, then 3, then 6, then 9, until we're out of atoms, or out of electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Like this. 1, 2, 3, 4, 5, 6, 7, 8. Now I draw little electrons, but we're going to draw them as dots. 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 electrons, 7 valence electrons, so chlorine gets 7 dots, starting at the 12 o'clock position and going once around before we double up. Always 1, 2, 3, 4 before we double up. Okay, so there's chlorine. Now, how many valence electrons does hydrogen have? Way up there. 1. To complete its octet, how many does it need?
8 or 7 more.
To complete hydrogen's octet, it needs 1 more. It needs a total of 2. Remember, hydrogen only has the S shell, so it can only hold 2. Everything else gets 8. So these are the rules. Each atom is going to share dots until it has an octet, except for hydrogen, which is only going to have 2 dots on one side. Pairs of sticks, or pairs of dots, will turn into sticks. And when an atom has unshared pairs, and I'll show you what that looks like, it keeps those unshared pairs. So we're going to do a couple examples after you write down the rules, if you want to write down the rules. Atoms are going to start with dots. We're going to arrange the dots together. I'm going to show you what that's going to look like in a minute or two. We're going to arrange the dots together until all the atoms have 8 dots, symbolizing a completed octet, except for hydrogen, which will have 2, symbolizing its completed shell. If an atom ever starts with bonding, or with unshared pairs, it keeps those unshared pairs. Let me show you what I mean. Sulfur how many electrons does sulfur have? How many valence electrons does sulfur have? 6. 1, 2, 3, 4, 5, 6. So sulfur is going to have 1, 2, 3, 4, 5, 6. Okay, and these electrons have labels. These two pairs of electrons are called unshared pairs. They're unshared pairs, meaning sulfur is going to keep those pairs to itself. It's not going to use them to bond. These are called bonding electrons. That one and that one. So sulfur can make 2 bonds. It has 2 bonding electrons. It has 2 unshared pairs representing 4 electrons. Those unshared pairs, it's going to keep to itself. The bonding electrons, it will give and take and share. Okay. Are you ready to see an example? This is actually really fun. Drawing Lewis structures is actually a lot of fun. So just watch the animation. You're going to have a chance to do your own. Just watch the animation. So this is what happens. We're going to draw methane. Now methane has a single carbon and 4 hydrogens. So we're going to write down the elements, and we're going to give them their dots. How many dots should hydrogens get? 1 dot. Where should it go? On the top. How many should carbon get? 4. So carbon gets 1, 2, 3, 4. Hydrogen gets 1 each. So again, carbon gets 1, 2, 3, 4. Hydrogen gets 1 each. Once we've drawn our dots around our elements representing the valence electrons, then we just arrange them until everything gets 8 except hydrogen, which gets 2. Like that. All right. So that's a rough sketch of methane. Methane has CH4. Carbon now has 2, 4, 6, 8, a completed octet. Hydrogen has 2, 2, 2, its completed shell. That's what methane is going to look like. Second. And then you're going to take the dots, and the dots are going to be represented by sticks. Bonding pairs get represented by sticks. Is that what you're going to ask? Okay. So once you've got your dots, you're going to replace the dots because these are called bonding pairs, pairs of electrons that are bonding. Remember, electrons, when they bond, or when atoms bond, they each give an electron. Fluorine says, I'll give you 1. The other fluorine says, I'll give you 1. Well, in this case, carbon says, I'll give you 1 hydrogen. Hydrogen says, I'll give you 1 carbon. So they have bonding pairs, pairs of electrons, and the bonding pairs get turned into sticks. That is the Lewis structure for methane. Questions? Okay. We'll do one more before we do some practice. Okay. Pick a non-metal up there. Anyone? Which one? Pick a non-metal of these guys right here. Pick a non-metal. Oxygen. Okay. So oxygen has how many valence electrons?
6.
1, 2, 3, 4, 5, 6. Let's bond oxygen with fluorine. Fluorine? How many does fluorine have? 1, 2, 3, 4, 5, 6, 7. And another fluorine, just so we can complete the molecule. 1, 2, 3, 4, 5, 6, 7. So fluorine has 3 unshared pairs. Unshared pair, unshared pair, unshared pair, unshared pair, unshared pair, unshared pair. Fluorine has 2 bonding electrons, or 1 bonding electron each. Those 2 are going to share, and those 2 are going to share. And what you're going to get is you're going to get oxygen and fluorine, it's going to look like that. So this fluorine is going to bond there. This fluorine is going to bond there. Oxygen will keep its unshared pairs. Fluorine will keep its unshared pairs. And the bonding electrons will turn into sticks. 1 and 2.
I thought the bond was on the left side of the fluorine.
It doesn't matter.
Doesn't matter.
Yeah. Once you actually make, drawing the dots is important, you go in order. But once you actually make the bonds, you can rotate them as however you need. Carson, did you have a question? Okay. Any other questions? Ready for some practice? Okay. Practice. So, you're going to follow the rules. There we go. Follow the rules. And what I'd like you to do is each of you, I'm going to turn the lights on, I'd like each of you to do these 5 molecules. When you are done, compare with your neighbor, or done with each one, compare it with your neighbor. And then I will choose 5 military volunteers to put their work on the board. So we move on. Now, double and triple bonds. Everything we've done so far are single bonds. If you find yourself with more bonding sites than you have valence electrons, then you can make double or triple bonds. It just happens when instead of sharing a single pair of electrons, atoms share 2 pairs of electrons. Now, some things will never make double bonds. Hydrogen has 1 electron, it will never make a double bond. The halogens have only 1 bonding electron, they can't make double bonds. Okay? But everything else can. So we drew carbon dioxide yesterday. You might have noticed it, might still be in your notes. But go ahead and take a look at it and see if you can draw carbon dioxide in your notes, realizing that carbon's going to be in the middle with oxygen on the outside. So give it a try. Try to draw carbon dioxide. Once again, oxygen starts with two unshared pairs. 2 pairs of unshared electrons. So oxygen's going to keep those unshared pairs. All right. So maybe those 2 bond. Maybe these 2 bond. Maybe these 2 bond. Oh, maybe these 2 bond. So what you end up getting is a molecule that looks like this. Now again, these dots can be top and bottom, left and right. It doesn't matter where oxygen's dots are, as long as it keeps them. Question?
Why do you think we thought those
You mean that?
Yeah.
I was going to.
Oh.
That was my next step.
Oh.
Yeah. So the 2 dots would become 2 arrows, or two lines. So that bonding pair and that bonding pair become 2 lines. That bonding pair and that bonding pair become 2 lines. And our end result looks like that. Okay, triple bond. The gas that mechanics use to melt things in the bottom of your car is acetylene. Acetylene has a triple bond. Go ahead and see if you can scribble acetylene out, realizing the carbons will be together. electrons together? So hopefully you caught something that looked like H, C, H, like that. That's acetylene. Not a lot of things make triple bonds. Pretty much carbon and nitrogen are it, and carbons and nitrogen's families. But that's about it. So you do need to realize they're there. Okay. Give me a thumbs up if this stuff's looking good to you. You got this. Okay. Any questions? Cool. All right, so we talked about polarity last time. When molecules are polar, the electrons are piled up somewhere or they are unsymmetrical. So when we use Lewis structures to determine polarity, the question we need to ask, which there's two questions we need to ask, are, is the molecule symmetrical and are the electrons piled up somewhere? Do I need to explain what the word symmetrical means? Yeah. Okay. Symmetrical means it can mirror over itself. Meaning, if you fold it, it's the same thing in any direction. That's a symmetrical molecule. Okay, so we talked about this last time, that water has two bond dipoles that add up to produce a molecular dipole. Ammonia also has three bond dipoles that add to be a molecular dipole. In determining if something is polar, the question we need to ask ourselves is it symmetrical? If the molecule is not symmetrical, it is polar. If the electron density has bunched up somewhere, it's also polar. Okay? So take a look at all the molecules you've drawn and see if you can identify which of them is polar. Make a little P next to it if it's polar. Look at all the molecules you've drawn today and put a little P next to it if it's polar. Put a little NP if you think it is nonpolar. So a polar molecule will be non-symmetrical. The electrons will have piled up, while a nonpolar molecule will be symmetrical. In a nonpolar molecule, the bond dipoles will cancel each other out. So when you've identified which things are polar, which things aren't polar, lean over to your neighbor and compare notes. See if you agree on which molecules are polar and which molecules are nonpolar. Take another 20 seconds. Okay, we're going to start from this side of the board and go across. If you think HCl is polar, raise your hand. Yeah, it's good. It's polar. And since it is polar, we're going to identify it as being polar by drawing a bond or molecular dipole partial negative. They have a little plus on the end that says, this is the plus end, that's the minus end. So yeah, HCl has a molecular dipole that points that way. If you think C2H5OH is polar, raise your hand. Polar? Non-polar. Good, polar, yep. And we're going to draw our bond dipole that direction again. Because the oxygen has these unshared pairs, the electrons have piled up on this side of the molecule. It is polar. H2O. If you think H2O is polar, raise your hand. Non-polar? Okay, it is superpolar. Oxygen is superpolar. So we have this big bunch up of electrons right there. Oxygen is very, very polar. Or sorry, water is very, very polar. Water is superpolar. We might have not written this one down, but do you think it's polar? It is. Here's the weird thing about this one. Where should you draw the dipole? What direction? Yeah, down. Because in this case, fluorine is actually more electronegative. This is kind of a dicey molecule. It wouldn't actually exist because fluorine is too electronegative. But for the purposes of our model, we'll leave it. Yeah.
I'm not getting this. I don't understand. I thought it was group number.
Okay. So back here, oxygen has two unshared pairs. A pair there and a pair there. Which means the electrons are piled up over here, making it unsymmetrical. Okay. So the idea is this side has more electron density. It's not symmetrical. If you flipped it over or folded it over itself, there's nowhere for it to fold. There's no other oxygen on this side. So it's unsymmetrical. Electrons are piled up over here, meaning this side has a partial negative where this side has a partial positive. That is a polar molecule. Do we need to do the other two, or do you got it?
No, I got it.
Okay. Stupid molecule doesn't exist. Carbon dioxide. This is a tricky one. If you think carbon dioxide is polar, raise your hand. If you think it is non-polar, raise your hand. Non-polar. Now, carbon dioxide is an excellent example of a test question, where the test question is usually something like this. All of these molecules have polar bonds. Which one is non-polar? Which molecule is non-polar? This has polar bonds. There's a polar bond there and a polar bond there. But those two polar bonds cancel each other out, so the molecule is non-polar. Carbon dioxide is non-polar. Even though it has polar bonds, those two polar bonds cancel each other out because you can fold the molecule over and it has symmetry. You take this side, fold it over, take this side, fold it over, you're going to get the same molecule. NH3. If you think NH3 is polar, raise your hand. Non-polar? It is polar. There's a bunch up of electrons right there making this molecule polar. Acetylene. If you think acetylene is polar, raise your hand. Non-polar? It is non-polar. Acetylene can be folded over, it is symmetrical. And lastly, C2H6. Polar? Non-polar. It is non-polar. You can fold it this way, and fold it this way, and it stays symmetrical, so it is non-polar. Okay, now would be a great time to ask questions. We're pretty much done for today. Okay, I'm going to give you the worksheet that I wanted to give you yesterday, but we didn't get to it. The lecture took too long. So you do have 12 minutes to work on the worksheet.